Imagine, if you will, that you are standing on the edge of a great, dark ocean. It is night. The water is still, stretching out toward a horizon that you cannot see. Behind you, the warm lights of your home are glowing, safe and familiar. But before you, there is only the vast, breathing silence of the sea. For thousands of years, we have stood on the shoreline of our own planet, looking out into the cosmic ocean, wondering if there are other lights, other islands, other homes out there in the dark. For most of human history, the answer was silence. We saw points of light, pinpricks in the velvet canopy of the night sky, but we did not know what they were. We named them gods and heroes and monsters. We charted their paths to plant our crops and navigate our seas. But we remained, as far as we knew, entirely alone. A single, solitary island of life in an infinite archipelago of dead stone and burning gas. But time changes our vision. Our eyes grew sharper. We built glass lenses to gather the faint light of the stars. We built great metal dishes to listen to the whispers of radio waves. And slowly, the dark ocean began to reveal its secrets. We learned that the stars are suns, billions of them, burning with the same nuclear fire as our own. We learned that the universe is not just vast, it is teeming with the potential for worlds. And then, very recently, in the span of a single human lifetime, something profound happened. We stopped guessing. We stopped dreaming without evidence. We started counting. We found them. The headlines were quiet at first, buried in scientific journals, obscured by data tables and light curves. But the cumulative weight of the discovery is staggering. Among the thousands of exoplanets, planets orbiting other stars that we have confirmed, there is a special, exclusive list. A collection of worlds that are not gas giants like Jupiter, nor frozen wastelands like Pluto, nor scorching hellscapes like Venus. We have identified 26 specific planets. 26 worlds that hold a terrifying and wonderful possibility. They are the best candidates we have ever found for harboring life. Tonight we are going to take a journey. We are going to leave the safety of our home lights. We are going to travel across the light years to visit these 26 worlds. We will walk their surfaces in our imagination. We will look up at their suns. We will breathe their atmospheres. We will ask the oldest question humanity has ever asked, but this time we will ask it with a map in our hands. The journey begins not with a rocket launch, but with a shift in perspective. To understand these 26 planets, we must first understand the silence that surrounded us for so long. Consider the Earth. It feels huge to us. It takes hours to fly across an ocean, months to walk across a continent. It feels permanent, stable, and central. But from the perspective of the universe, Earth is dust. It is a microscopic speck caught in a sunbeam. For centuries, this fragility terrified us. If we are just dust, does our life matter? But there is another way to look at it. If Earth is just a rock made of common elements, silicon, iron, oxygen, carbon, and if our sun is just a star, a common yellow dwarf, then there is nothing miraculous about our existence. There is only statistics. If the ingredients are common and the kitchen is infinite, then the recipe must have been cooked more than once. This is the hope that drives the astronomers. It is a quiet, mathematical hope. It is the belief that nature does not make unique things. Nature makes multiples. Nature repeats itself. When we look at the 26 planets we are discussing, we are not looking for exact duplicates of Earth. We are looking for echoes. We are looking for the rhyme of history. We are looking for places where the conditions are just right for the delicate chemistry of life to begin its long, slow dance. The search began in earnest only a few decades ago. Before the 1990s, we did not know for sure if there were any planets outside our solar system. We assumed they were there, but we had no proof. The stars are so bright and planets are so small and dim that seeing them is like trying to spot a firefly hovering next to a searchlight seen from 1,000 miles away. But we found ways to look. We learned to watch the stars for the tiny, rhythmic dimming that happens when a planet crosses in front of them, a mini eclipse. We learned to watch the stars for the subtle wobble caused by the gravity of an orbiting world tugging on its parent sun. and the floodgates opened. First, we found the giants, massive hot Jupiters orbiting incredibly close to their stars. Worlds so strange they shattered our theories of how solar systems form. Then, as our instruments became more sensitive, we began to find smaller worlds, Neptunes, super-Earths. And finally, rocky worlds. Worlds the size of home. The number of confirmed planets climbed. Dozens became hundreds. Hundreds became thousands. The Kepler Space Telescope, a lonely watcher drifting in the dark, stared at a patch of sky in the constellation Cygnus for years, unblinking. It returned a treasure trove. It told us that planets are everywhere. There are more planets in the Milky Way galaxy than there are stars. Let that sink in. There are more worlds than there are suns. The night sky is not empty, it is crowded, but quantity is not quality. Most of these worlds are hostile. Some are so close to their stars that their surface is molten lava, raining rocks and iron. Others are so far away that their atmosphere has frozen solid, collapsing onto the surface in drifts of nitrogen snow. Some are blasted by radiation so intense it would strip away our DNA in seconds. We are not looking for just any world, we are looking for the Goldilocks worlds. The ones that are not too hot, not too cold, the ones that are just right. Out of the thousands of candidates, astronomers have filtered, analyzed, and debated. They have peered at the data, looking for the telltale signs of habitability. And from this rigorous process, a list has emerged, a list of high-interest targets. 26. It is a small number. You can count it on your fingers and toes with a few left over. But consider what that number means. If even one of these worlds has life, even the simplest microscopic slime, even a single cell dividing in a warm alien ocean, it would change everything. It would mean that we are part of a community. It would mean that the universe is not a sterile void, but a garden. And if one of them has complex life, if one of them has forests or creatures that swim and fly, if one of them has eyes that look up at their own moon and wonder if they are alone. The 26 planets are scattered across our local neighborhood of the galaxy. Some are relatively close, just a dozen light-years away. Neighbors, in cosmic terms. Others are thousands of light-years distant, visible only as shadows against distant fires. They orbit different kinds of stars. Some orbit stars like our Sun, yellow and steady. Others orbit red dwarfs, small, cool stars that will burn for trillions of years long after our Sun has died. This variety is important. It tells us that life might not be limited to one specific type of environment. It might be adaptable. It might be waiting in places we never thought to look. As we prepare to examine them, we must quiet our minds. We must slow down our own internal clocks. The distances between these worlds are incomprehensible to our daily experience. To travel to the nearest of them with our fastest current rockets would take tens of thousands of years. We cannot go there in the flesh, not yet, but we can go there in the mind. We can use the data we have, the mass, the radius, the orbital period, the temperature to build a picture. We can paint the landscape with the brush of science. So, let us relax. Let the worries of the day fade away. Let the noise of the earth recede. We are lifting off. We are drifting up through the blue atmosphere into the black velvet of space. The earth shrinks below us, a blue marble, then a pale blue dot, and then it is gone. We are floating in the interstellar medium. It is quiet here, peaceful. There is no wind, there is no sound, only the steady, unblinking light of the stars. We are drifting toward the constellation of Aquarius, toward the constellation of Cygnus, toward the constellations of Libra and Dorado. We are going hunting for life. The first step in understanding these 26 worlds is to understand the filter. How did we choose them? What makes them special? Why these 26 and not the thousands of others? It comes down to a concept called the habitable zone. It is a band of space around a star, a shell of possibility. Closer to the star, water boils away into steam. Further out, water freezes into ice. But in the middle, in that narrow, precious band, water can exist as a liquid. Liquid water. It is the master key. As far as we know, life needs a solvent. It needs a medium in which chemicals can mix, react, and form complex chains. Water is the perfect medium. It is abundant, it is stable, it is magic. Every one of the 26 planets we will discuss resides in or very near this habitable zone. They are the worlds where rain might fall. They are the worlds where rivers might carve canyons through the rock. They are the worlds where oceans might rise and fall with the tides of alien moons. But being in the habitable zone is not enough. The moon is in the habitable zone, and it is dead. Mars is on the edge of the habitable zone, and it is a dry, frozen desert. To be truly habitable, a planet needs more. It needs an atmosphere. It needs a magnetic field to protect it from the stellar wind. It needs a solid surface. The 26 planets on our list are primarily rocky worlds. They are terrestrial. They have a crust, a mantle, a core. They are places you could stand. Imagine the feeling of gravity on a world slightly larger than Earth. You would feel heavier, your movements more deliberate. Imagine the feeling of gravity on a world slightly smaller. You would feel light, buoyant, as if you could jump over a house. We are going to visit worlds with 2 suns. We are going to visit worlds where the year lasts only a few days. We are going to visit worlds that are locked in an eternal stare with their star, one side forever day, one side forever night, with a twilight zone in between where life might thrive in the endless sunset. This is the promise of the 26. They are not just data points. They are places. Real, physical places, existing right now as you listen to this. At this very moment on one of these worlds, a wind might be blowing through a valley of red stone. At this very moment, waves might be crashing on a shore of black sand. At this very moment, a creature might be opening its eyes to greet a dawn that is redder or dimmer or brighter than our own. The universe is waiting. The silent ocean is rippling. Let us wade in. We begin our exploration by descending into the details, drifting slowly toward the first cluster of possibilities. To understand the 26, we must appreciate the delicate balance of their existence. It is not enough to simply be a rock in space. A planet is a complex system, a machine of energy and matter, constantly processing the light of its star. The scientists who compiled this list, astronomers from the University of Puerto Rico at Arecibo, researchers from the Max Planck Institute, teams analyzing data from NASA's Kepler and TESS missions. They use a metric called the Earth Similarity Index, or ESI. Think of the ESI as a score. Earth is a 1, 0, a perfect match. A rock floating in deep space with no atmosphere is close to 0. The 26 planets we're interested in have high scores, often above 0. 8. They are the siblings and cousins of our home. Let us travel first to a system that has captured the imagination of everyone who has seen the data. Let us travel to the star known as Kepler 452. It is a long journey. Kepler 452 is about 1,400 light-years away from Earth, in the direction of the constellation Cygnus, the Swan. We drift through the spiral arm of the galaxy, passing nebulae where new stars are being born, passing clusters of old stars dying in slow motion. We arrive at the star. It is a G-type star, very similar to our own Sun. It is roughly the same temperature, roughly the same mass. If you were floating in space nearby, it would look reassuringly familiar. A bright, yellow-white ball of plasma. It is slightly older than our Sun, perhaps by 1.5 billion years. It is a wiser, more mature star. And orbiting this star, in a path that takes 385 days to complete, almost exactly the same length as an Earth year, is the planet Kepler 452b. This planet is often called Earth's cousin. It is the first near-Earth-size world found in the habitable zone of a star that is so similar to our own. Let's descend. Kepler 452b is larger than Earth. It is a super-Earth, with a radius about 60% wider than our planet. This means it has more mass. If you were to stand on the surface, you would weigh about twice what you weigh on Earth. The gravity would pull at you, a constant heavy embrace. You would feel grounded, solid. Because the star is older, it is slightly brighter than our Sun. The planet receives about 10% more energy than Earth does. This suggests a warmer world. If Kepler 452b has an atmosphere similar to ours, it might be a greenhouse world, sliding toward the runaway heating that destroyed Venus. But if it is massive enough, its volcanoes might still be active, churning out gases, regulating the climate. Imagine standing on a high plateau on Kepler 452b. The sky above you is thick. The higher gravity holds onto the atmosphere tightly, creating a dense blanket of air. The light from the sun is bright, golden, perhaps a little harsher than what we are used to. Because the planet is older, it has had more time for life to evolve. If life began here at the same time it began on Earth, it would be 1 billion years ahead of us. Look at the horizon. The geology here might be similar to Earth with silicates and granite, but the erosion would be different. The weather patterns on a super Earth are likely more intense. Thicker air means stronger winds. The oceans, if they exist, might be shallower but broader, covering vast stretches of the planet in a warm global sea. Can you see the plants? If photosynthesis evolved here, the leaves might not be green. To deal with the slightly more intense radiation and the different spectrum of the star, vegetation might be yellow or orange, reflecting the excess light. Imagine a forest of tall, thick-trunked trees needed to support themselves against the double gravity, with canopies of amber leaves rustling in a dense, warm wind. It is a world of summer, an eternal, heavy summer. We leave Kepler 452b, rising back into the silence, and turn our gaze to another candidate, one that offers a completely different vision of a habitable world. We are traveling to the system known as Kepler 196. This is closer, about 500 light-years away. But the star is different. It is an M dwarf, a red dwarf star. It is barely half the size of our Sun and much cooler. It glows with a ruddy, ember-like light. Red dwarfs are the most common stars in the universe. If life exists, statistically, it probably lives around a red dwarf. Here, we find Kepler 186f. This planet is special because of its size. It is less than 10% larger than Earth. It is, for all intents and purposes, an Earth twin in size. The gravity here would feel familiar. You could walk comfortably, you could run. But the light is where the dream changes. Kepler 186 orbits its star at a distance that would be inside the orbit of Mercury in our solar system. It is huddled close to the fire for warmth. Because the red dwarf is so cool, the habitable zone is tight and close. A year on this planet lasts only 130 days. Stand on the surface of Kepler 86f. It is noon. But the sky is not blue. The star produces very little blue light. The atmosphere, scattering the longer wavelengths, might appear white or pinkish tan. The sun itself, hanging large in the sky, is a pale orange orb. It is never fully bright here in the way we understand it. Noon on Kepler 186f looks like an hour before sunset on Earth. It is a world of perpetual twilight, of long shadows and soft diffused illumination. How would life adapt to this? Plants here would be starving for photons. They would need to absorb every scrap of light that falls on them. They would likely be black, or perhaps a deep, dark purple. Imagine a meadow of jet black grass, absorbing the weak red light of the sun. Imagine flowers that open wide, dark petals to catch the warmth. It is a Gothic garden, beautiful and somber. Because the planet is so close to its star, there is a danger. Red dwarfs are known to be volatile, prone to violent solar flares that can scour the atmosphere of nearby planets. But Kepler 186 is a calm star. It is old, it has settled down. This planet may have had billions of years of peace. There is another possibility for these red dwarf worlds: tidal locking. When a planet orbits very close to a star, the gravity can lock its rotation. The same side of the planet always faces the star, just as the same side of the moon always faces the Earth. If Kepler 186f is tidally locked, then there is no day and night. There is only the day side, forever baking under the red sun, and the night side, forever frozen in eternal darkness. But in between, along the terminator line, the border between day and night, there would be a ring of eternal dawn. This is where life would cling. Imagine living in that strip of twilight. The sun sits forever on the horizon, never rising, never setting. The temperature is constant. Winds blow from the hot side to the cold side, creating a continuous breeze that circulates heat and moisture. The civilization, if there were one, would live in the lands of the long shadow. They would never know the changing of the seasons. They would only know the stability of the red sun on the horizon, the lighthouse that never sleeps. We drift away from the red twilight, moving on to another member of the 26. Let us consider the Teegarden star system. This is a neighbor. Only 12 light-years away, in cosmic terms, it is right next door. If we had a fast enough ship, we could almost imagine going there within a few generations. Teegarden's star is an ultra-cool dwarf, a tiny star barely bigger than Jupiter, though much more massive. It burns slowly, so slowly that it will outlive the current age of the universe 1,000 times over. Here, we found two planets, Teegarden B and Teegarden C. Both are Earth mass. Both are potentially habitable. Teegarden B is the innermost one. It orbits the star in just 9 days. A year passes in less than a week. The pace of life here would be frantic if it followed the celestial cycles. But again, let us look closer. Teegarden B has the highest Earth similarity index of almost any planet discovered. It is 95% similar to Earth in terms of its bulk properties. Because the star is so dim, the planet must hug it tightly to stay warm. The view from the surface would be dominated by the star. It would look 3 times larger than our sun does in our sky. A massive looming presence. But here is the beauty of the Teegarden system. The star is quiet. For a red dwarf, it is remarkably stable. This means the atmosphere of Teegarden B might be intact. It might have clouds. It might have rain. The temperature on the surface is estimated to be roughly 28 degrees Celsius, or about 82 degrees Fahrenheit. It is temperate. It is comfortable. It is a shirt-sleeve world. If you stood there, on a rocky outcrop overlooking a shallow sea, you would feel at home. The gravity is almost exactly 1 Earth gravity. The temperature is balmy. The only difference is the color of the light and the stillness of the sun in the sky. It is strange to think that such a place exists just 12 light-years away. While we were building pyramids, while we were fighting wars, while we were inventing the internet, this world was there. Sitting in the dark, warm and wet, waiting to be noticed. Maybe there are oceans there. And where there are oceans, there are shores. And where there are shores, perhaps there are things that crawl out of the water to lay their eggs in the sand. As we ponder Teegarden B, we must address the nature of these Goldilocks conditions. It is not just about temperature, it is about time. Our sun is about 6 billion years old. It has roughly 5 billion years left before it swells into a red giant and consumes the Earth. But red dwarfs like Teegarden's star, they can burn for trillions of years. This means that planets like Teegarden B are long-term real estate. If life starts there, it has an eternity to evolve. It is not racing against the death of its star. Perhaps the oldest civilizations in the universe are not around bright yellow stars like ours, but huddled around the dim, immortal red dwarfs. Perhaps they have watched galaxies collide and stars burn out, safe in their slow red sanctuaries. These are just the first steps into the list of 26. We have seen a heavy summer world. We have seen a dark twilight garden. We have seen a nearby neighbor with a perfect temperature. But the galaxy is creative. The variations are endless. As we prepare to move deeper into the list, we will encounter worlds that challenge our definitions of what a planet can be. We will see ocean worlds. We will see trapped worlds. We will see systems with 7 siblings all crowded together in a cosmic dance. The silence of the ocean is broken by these islands of possibility. We are charting the archipelago, and the journey is only just beginning. Rest now, in the space between the stars. Let the image of the red sun and the black grass fade gently. Let the feeling of the heavy gravity of Kepler 452b lift from your shoulders. We are floating again, weightless, drifting toward the next wonder. We are drifting again. We leave the single red suns behind and move deeper into the dark, searching for something that defies our expectations of solitude. In our own solar system, Earth sits alone in the habitable zone. Mars is too cold, Venus is too hot. We are an only child, playing in the perfect spot of the garden. But the universe is fond of families. It is fond of abundance. About 40 light-years from Earth, in the constellation of Aquarius, there is a star that is barely a star. It is an ultra-cool red dwarf known as TRAPPIST-1. It is small, only slightly larger than Jupiter, and it glows with a dim ruby light. If you were standing on a planet orbiting it, the star would look like a glowing ember, casting a salmon-pink light across the landscape. For a long time, this star was just a faint dot in our telescopes. But then, we looked closer. And what we found there changed the way we think about the architecture of solar systems forever. We did not find one planet, we did not find 2 or 3, we found 7. 7 Earth-sized worlds huddled close together around that tiny warm fire. And of those 7, 3 of them, TRAPPIST-1a, F, and G, are firmly inside the habitable zone. Imagine a solar system that fits inside the orbit of Mercury. Imagine worlds so close to each other that if you stood on the surface of one, you could look up and see the others floating in the sky, not as points of light, but as full, round disks. You could see their clouds, you could see their continents. They would look as large as the moon looks to us, sometimes larger. It is a crowded sky, a sky of siblings. Let us descend toward the middle sibling, the planet known as TRAPPIST-1. This world is the most Earth-like of the bunch in terms of density and size. It receives about the same amount of light from its star as Earth does from the Sun. As we approach, we see that this is likely a rocky world. It has a heavy iron core, but the view from the surface is unlike anything on Earth. Because the planets are so packed together, they interact with each other. Their gravity tugs and pulls in a rhythmic dance. This is called orbital resonance. For every 8 times the inner planet orbits, the next one orbits 5 times, the next one 3, and so on. It is a mathematical harmony, a music of the spheres. Standing on TRAPPIST-1e, you would feel this rhythm. The tides here would be complex, pulled not just by the star but by the sister planets passing overhead. The oceans, if they exist, would heave and sigh in strange syncopated patterns. Let us walk along a coastline on TRAPPIST-1e. The light is dim, ruddy, and eternal. Like many red dwarf planets, it is likely tidally locked. The sun never moves. It hangs in the sky, a permanent guardian. But look up. Drifting slowly across the twilight sky is TRAPPIST-1f. It is huge, a swirling marble of white and blue. You can see the storms moving across its face. You are looking at another world, another potential home for life, and it feels close enough to touch. And behind it, rising from the horizon, is TRAPPIST-1g, another sister, another world. The psychological impact of living in such a system would be profound. On Earth, we felt alone for thousands of years. We had to imagine aliens, but for any civilization that might arise on a TRAPPIST world, they would never be lonely. They would just have to look up. The concept of us and them would be different. The drive to build spaceships would be irresistible. A journey to another planet here would not take months, it would take days. But is there life? The TRAPPIST system is old. It is nearly twice the age of our solar system. These planets have had nearly 8 billion years to evolve. 8 billion years of the star glowing steadily. 8 billion years of the tides washing against the shores. If life began here, it has had time to become something we cannot even comprehend. But there is a challenge. The early years of a red dwarf star are violent. They flare and rage. It is possible that the atmospheres of these worlds were stripped away billions of years ago. It is possible they are dry, dead rocks, baked by the radiation of their youth. However, recent models suggest that they might have started with immense amounts of water. Far more water than Earth. If they lost 90% of their water, they might still have deep global oceans. This leads us to the next world in the chain, TRAPPIST-1f. This planet is slightly larger, slightly cooler. It might be an eyeball Earth. Imagine a world covered entirely in ice, except for a large, open pupil of liquid ocean directly facing the star. In this open ocean, the water is perpetually warm. The surrounding ice walls would rise kilometers into the air, reflecting the red light. The ecosystem here would be entirely aquatic. Swimming in those waters beneath the red sun, life would be shielded from the flares, shielded from the cold. It would be a womb, dark, warm, and safe. And then there is TRAPPIST-1G, the outer sibling of the habitable trio. It is colder here. It receives about the same amount of light as Mars. On Earth, this would be a frozen wasteland. But if TRAPPIST-1G has a thick atmosphere of carbon dioxide, a super greenhouse effect could keep it warm. It might be a world of dense fog, a world where you can never see the stars, only the diffuse glow of the red sun filtering through miles of cloud. On the surface, it would be dim and humid. Giant fungi might grow here, towering spires of soft tissue reaching up into the mist, feeding on the chemical energy of the air. The Seven Sisters are a mystery. We have pointed our best telescopes at them. The James Webb Space Telescope is currently sniffing their atmospheres, looking for carbon dioxide, looking for methane, looking for water vapor. We are listening to the silence of the Seven Sisters, waiting for a whisper. But while we wait, let us consider the implication of their existence. The universe made 7 Earth-sized planets in one system. It packed them in like sardines. It suggests that making rocky planets is easy. It suggests that nature wants to make worlds. If the TRAPPIST system is common, then there are billions of such families in our galaxy alone. Billions of skies filled with sister moons. Billions of tides pulled by neighbor worlds. We linger here for a moment, in the red twilight of TRAPPIST-1e, watching the great disk of TRAPPIST-1e set behind a range of dark mountains. It is a view that belongs on the cover of a science fiction novel, yet it is real. It is physics. It is gravity. It is there, right now, 40 light-years away, spinning in the dark. We leave the crowded family of Aquarius and set a course for something different. We are going to challenge our own ego. For a long time, we have assumed that Earth is the perfect standard. We call it Earth-like when we find a good planet. We assume that to be habitable, a planet must be just like ours. A yellow star, a 24-hour day, a single moon. But what if Earth is not the best? What if Earth is merely good enough? Scientists have begun to model a class of planets that they call superhabitable. These are worlds that are potentially better for life than Earth is. Worlds that are richer, warmer, wetter, and more stable. We are traveling now to a planet candidate known as KOI 571501. It is far away, nearly 3,000 light-years. But the data tells us a fascinating story. The star is a K-dwarf. K-dwarfs are the Goldilocks stars of the universe. They are smaller and cooler than our Sun, but larger and warmer than the red dwarfs. They strike a perfect balance. Our Sun burns for about 10 billion years. That is a long time, but it is a limit. A K-dwarf can burn for 40 to 70 billion years. It offers a stability that our Sun cannot match. It does not flare like a red dwarf. It just shines, steady and true for eons. The planet KOI 571501 is located in the prime habitable zone of this gentle star, and it fits the criteria for superhabitability perfectly. It is likely about 8 times the mass of Earth. This extra mass is crucial. It means the planet stays hot on the inside for longer. Plate tectonics, the recycling of the crust that regulates our atmosphere, would last longer. The magnetic field would be stronger, a better shield against the cosmos. A superhabitable world is also likely to be slightly warmer than Earth, perhaps by about 5 degrees Celsius. This sounds like global warming to us, and on Earth it is a problem. But on a planet designed for it, it means no ice caps. It means a tropical world. Imagine a planet that is a global archipelago. thousands of islands scattered across shallow, warm seas. The biodiversity on Earth is highest in the tropics. On a super-habitable world, the tropics stretch from pole to pole. There are no deserts. The extra gravity holds a thicker atmosphere, smoothing out the temperatures. The moisture is distributed evenly. It is a planet of rainforests, of coral reefs, of endless, teeming life. If we could stand on KOI 5715.01, the air might feel rich and heavy in our lungs. The oxygen levels could be higher. The sky might be a slightly different shade of blue, perhaps leaning toward turquoise. The vegetation would not struggle. On Earth, plants fight for space and light. On a super-habitable world, the biomass, the sheer amount of living stuff, could be 10 times greater. Trees that grow a kilometer high, ferns the size of cathedrals. It humbles us. We look for a second Earth, but we might find a paradise that makes Earth look like a dry, struggling frontier. But the list of 26 contains other strange possibilities. We must visit the water worlds. Let us turn our gaze to Kepler 62f. It sits 1,200 light-years away. It is a super-Earth, about 40% larger than our home. And models suggest it might be covered entirely in water. Not an ocean like the Pacific, which is a thin skin of water over rock, but an ocean that is hundreds of kilometers deep. An ocean where there is no bottom, only a transition from liquid water to exotic high-pressure ices. No continents, no islands, no dry land. What would life look like here? On Earth, the whales are the largest creatures because the water supports their weight. On Kepler 62f, without land to limit them, could creatures grow even larger? Imagine living islands, mats of vegetation miles wide floating on the surface, drifting with the currents, entire ecosystems living on the backs of these rafts. Imagine creatures that never know the concept of down or ground. They live in a three-dimensional, endless blue. The weather on a water world would be predictable but powerful. Without mountains to break the wind, storms could travel around the planet forever, building momentum. But beneath the waves, in the deep silence, life would remain undisturbed. And then there is the most tantalizing neighbor of all, the one that is right outside our window. Proxima Centauri, B. It is the closest exoplanet to Earth. 2 light-years away. If we ever send a probe to another star, this will be the first destination. Proxima b orbits a red dwarf. It is Earth-sized. It is in the habitable zone. For years we debated if it could hold an atmosphere. The star is active, it spits flares that are terrifying in their power. We feared Proxima b was a dead rock, stripped bare by the fury of its parent. But recent studies have given us hope. If the planet has a strong magnetic field, or if it formed with a massive amount of water, it could survive. Let us imagine the surface of Proxima b. The light is dim red. The star is huge. The planet is likely tidally locked. But there is a wind that never stops. It blows from the hot side to the cold side. The landscape is shaped by this wind. The rocks are scoured and polished. The plants here, if they exist, might crouch low to the ground to avoid the gale. They might have hard shells like tortoises. They might be stone plants looking like rocks until they bloom. Because it is so close, we can dream of Proxima b more vividly than the others. We can imagine the day when a small robotic sail pushed by lasers from Earth zips past this world and sends back a blurry photo, a photo of a blue pixel or a green one. That single pixel would change human history. The 26 planets are not just destinations, they are mirrors. They show us what is possible. They show us that the recipe for life can be tweaked, altered, and improved. We have seen the crowded sisters of TRAPPIST. We have seen the tropical paradise of the superhabitable worlds. We have seen the endless oceans of Kepler 62. And we realize that the Goldilocks zone is not a line. It is a spectrum. It is a vast grey area where chemistry turns into biology. As we finish this leg of the journey, we hang suspended in the void between the spiral arms of the Milky Way. We look back at the path we have traveled, from the heavy summer of Kepler 452b to the red twilight of Proxima. The galaxy feels different now. It is no longer just stars. It is a collection of environments, a collection of potential homes. We are not just looking for life, we are looking for kin. And as we prepare for the final leg of our journey, we must ask the hardest question of all. If there are so many homes, if the conditions are so right, where is everyone? Why is the radio silence so deafening? We will explore this silence and the final, most mysterious worlds on our list as we conclude our voyage. The silence of the cosmos is heavy. We have traveled to the heavy summer of Kepler 452b. We have walked the twilight zones of the red dwarf worlds. We have floated on the endless oceans of Kepler 62f. In our minds, we have populated them with forests, with creatures, with civilizations. But in reality, we have not yet heard a sound. We have not picked up a radio signal. We have not seen a spaceship. The 26 planets are silent. So, how do we know? How do we bridge the gap between could have life and does have life? We do not need to go there to find out. We do not need a warp drive. We just need light. Every time a planet passes in front of its star, a tiny fraction of the starlight passes through the planet's atmosphere on its way to Earth. It grazes the edge of the world, and as it passes through the air, the chemicals in that atmosphere steal little pieces of the light. Oxygen steals a specific color. Methane steals another. Carbon dioxide, water vapor, ozone. They all leave their fingerprints. They sign their names in the spectrum of the light. This is the new frontier. We are no longer just planet hunters, we are atmosphere sniffers. Right now, the James Webb Space Telescope is staring at these 26 worlds. It is collecting those faint, stolen photons. It is building a catalogue of alien air. What are we looking for? We are looking for disequilibrium. On a dead world, the chemistry is boring. It settles down. Carbon dioxide and nitrogen just sit there reacting slowly or not at all. But on a living world, the chemistry is wild. Life messes things up. Life produces waste. If we look at Earth from deep space, we see oxygen and methane together. In a standard chemical model, they should react with each other and disappear. The fact that they are both there means something is constantly replenishing them. Something is breathing. Something is rotting, something is living. This is the biosignature. Imagine the moment, perhaps a few years from now, perhaps tomorrow. A team of astronomers is looking at the data from one of our 26 candidates. Maybe Luyten b, a massive rocky world just 12 light-years away. They see the dip in the light, they analyze the spectrum, and they see it. The spike of oxygen, the spike of methane, the hint of chlorophyll. They would not see a city, they would not hear a song, but they would know with mathematical certainty that the rock is alive. But there is a deeper layer to this search. We are not just looking for biology. We are looking for technology. This is the search for technosignatures. If a civilization on one of these 26 worlds is advanced enough, they might have polluted their atmosphere. We might see chlorofluorocarbons, industrial chemicals that nature does not produce. We might see the glow of artificial lights on the night side of the planet. We might see immense structures, solar panels covering continents to harvest the energy of their red sun. We have listened to these 26 worlds with radio telescopes. We have pointed the great dishes at them and tuned across the frequencies, listening for the hum of a broadcast, the rhythmic pulse of a radar, the static of a television show. So far, nothing. But the silence might not mean emptiness. It might simply mean we are listening to the wrong frequency. Or it might mean that civilizations do not use radio for long. Or perhaps they are simply quiet. There is a concept called the Great Filter. It suggests that life is rare because it is hard to survive. Maybe planets are common, but life is hard to start. Or maybe life starts often, but intelligence destroys itself. When we look at the 26 planets, we are looking at survivors. They have survived the chaos of their formation. They have survived the bombardment of asteroids. They have maintained their orbits for billions of years. If life is there, it is resilient. Consider the planet LHS 1140b. It is another rocky super-Earth in the habitable zone of a red dwarf. It is dense, made of rock and iron. It is a fortress of a world. If life exists there, it has evolved under a gravity 4 times stronger than Earth's. It would be tough, low to the ground, robust. It would have survived for 5 billion years. If we found a microbe on LHS 1140b, it would be our elder. It would carry a genetic history longer than the history of our entire solar system. We are new to this neighborhood. We are the children of the galaxy. Our sun is young. Our planet is young. We have only just opened our eyes. The 26 worlds have been spinning in the dark for eons, waiting for us to wake up and notice them. The light that reaches our telescopes from Kepler 442b left that planet 1,200 years ago. We are seeing it as it was when the Vikings were sailing the seas of Earth. We are looking into the past. If we see a signal today, they sent it when we were building castles of stone. If we send a reply today, they will receive it when we have become something else entirely. The distances are vast, but the connection is real. We are bound to these worlds by the laws of physics. We are made of the same stardust. We are drinking from the same cosmic well. The search for biosignatures is the most profound scientific endeavor in human history. It is the search for a mirror. We want to know if the universe is alive, because if it is, then we are not an accident. We are a pattern. And if we find life on just one of these 26 worlds, just one, the number changes from 1 to 2. And in mathematics, once you have 2, you have infinity. If it happened twice, it happens everywhere. We have come a long way. We have traveled through the light years. We have stood on the shores of super-habitable oceans. We have walked under the 7 moons of TRAPPIST. We have felt the heavy gravity of the super-Earths and the red warmth of the dwarf stars. And now, we return. We drift back through the silence, past the nebulae, past the clusters, back toward the small yellow star that we call the Sun. We see the familiar blue marble rising in the darkness. Earth. It looks different now, doesn't it? Before we left, Earth seemed unique. It seemed like a lonely miracle, a solitary raft in a dead ocean. But now, as we descend through the clouds, we carry with us the knowledge of the 26. We know that out there, in the dark, there are cousins, there are siblings, there are clouds raining on other mountains, there are waves crashing on other beaches. There are winds whispering through valleys that no human foot has ever trod. The universe is not a void. It is a canvas, and it has been painted with a lavish hand. The discovery of these 26 planets is a turning point for our species. It marks the end of our cosmic childhood. We are no longer the center of existence. We are simply one member of a vast and diverse family of worlds. It brings a sense of humility. We are not the masters of the universe, we are its inhabitants. But it also brings a sense of comfort. We are not alone in the dark. Even if we never hear a radio signal, even if we never shake the hand or tentacle of an alien, just knowing that the places exist is enough. Just knowing that the conditions for life are not a fluke, but a feature of the universe, changes how we feel when we look up at the night sky. Tonight, when the sun sets and the stars come out, go outside, look up. You are not looking at a ceiling of static lights. You are looking at a map. You are looking at a geography of potential. Find the constellation of Aquarius. Somewhere in that direction, the 7 sisters of TRAPPIST are dancing their complex gravity-bound waltz. Find the constellation of Cygnus. Somewhere in that direction, the heavy summer world of Kepler 452b is basking in its ancient sunlight. Find the constellation of Lyra. Somewhere there, the super-habitable paradise of KOI 575Phi is teeming with life we can only imagine. They are there. They are real. 26 worlds, and those are just the ones we have found so far. Those are just the ones that happen to blink at us in the right way, at the right time. For every one we found, there are millions we missed. The 26 are the ambassadors. They are the first few islands emerging from the mist. Behind them lies a continent. We are living in the golden age of discovery. For thousands of years, our ancestors could only wonder, We are the first generation to know. We know that the universe is wet. We know that the universe is rocky. We know that the universe is warm. We found 26 planets that could have life, and in finding them, we found something else. We found a future. A future where we are not trapped on a single rock, but where we are explorers in a galaxy teeming with wonder. The ocean is not silent anymore. If you listen closely, with the ear of science and the ear of the imagination, you can hear it. The gentle lap of waves on a distant shore. The rustle of alien leaves in a red twilight. The breath of a cosmos that is waking up. We are not alone. We never were. Sleep well, inhabitants of Earth. The stars are watching over you, and you are watching back. The connection is made. The journey has begun. The journey to the 26 planets has, until now, been a journey of the mind. We have used data points on a graph, dips in brightness, wobbles in a star's motion, to construct these worlds in our imagination. We have seen them through the lens of mathematics. But the human spirit craves more than data. It craves sight. We want to see the clouds. We want to see the continents. We want to take a picture that is not just a pixel but a portrait. As we move forward into the middle of the 21st century, a new generation of cathedrals is being built. They are not made of stone and stained glass, but of beryllium, gold, and ultra-smooth mirrors. They are the great glass eyes that will open in the silence of space. For decades, we relied on the Hubble Space Telescope. Then came the James Webb, unfolding its golden honeycomb to see the heat of the universe. But to truly see the 26 planets, to see them as worlds, we need something even grander. We are building the Habitable Worlds Observatory. Imagine a telescope so large that it cannot be launched in one piece. It must be folded like an intricate origami flower, or perhaps assembled by robots in the quiet vacuum of high Earth orbit. Its mirror is vast, a collecting pool for light that has traveled for centuries. But size is not the only challenge. The problem with seeing a planet next to a star is the glare. The star is billions of times brighter than the world orbiting it. It is like trying to see a firefly hovering next to a lighthouse beam while standing 10 miles away. To solve this, we need a shadow. We are designing the star shade. Imagine a giant flower, the shape of a sunflower, floating in space tens of thousands of kilometers away from the telescope. It is perfectly shaped to block the light of the star while letting the light of the planet pass around its edges. When the telescope aligns with the star shade, the star disappears. The blinding glare vanishes. And there, popping out of the darkness, are the planets. Kepler 452b appears not as a graph, but as a dot of color. Teegarden B appears as a ruby speck. And if we stare at them long enough, collecting photon after photon, we might see something extraordinary. We might see the glint of an ocean. This is not science fiction. This is the glint. Sunlight reflecting off liquid water. If we see the glint, we know there is a surface ocean. We know there are waves. And as the planet rotates, we might see the color change. Blue for ocean, brown for rock, white for clouds, and green. Green. The most exciting color in the universe. If we see a periodic darkening and brightening that matches the rotation of the planet, and if the spectrum tells us it is vegetation, we will have found the first alien forests. We might not know what the trees look like. We might not know if they have leaves or needles, or if they are purple or red, but we will know they are there. The Habitable Worlds Observatory will turn the 26 candidates into neighbors. It will map their weather. It might even detect their seasons. Imagine watching the winter ice caps grow on a world 1,000 dread light years away. Imagine watching the green flush of spring spread across a southern continent on a super Earth. This is the patience of astronomy. We build these machines not for ourselves, but for the next generation. The astronomers who will use these instruments are currently in elementary school. They are looking up at the plastic stars on their bedroom ceilings, unaware that they will be the ones to map the geography of Proxima Centauri b. But even with the greatest telescope, we are still just looking. We are still just ghosts peering through a window. The ultimate dream, The dream that has driven humanity since we first walked out of Africa is to go there, to cross the void. The distances are crushing. To reach Proxima b with our current chemical rockets would take 70,000 years. Empires would rise and fall on Earth while the ship was still in the dark. But we are learning to sail on a new kind of wind. We have looked at the 26 worlds, we have listened to them, we have analyzed them. Now, let us dream of touching them. The project is called Breakthrough Starshot. The idea is simple, elegant, and audacious. We cannot send a massive ship. It is too heavy. It takes too much energy to push. So, we make the ship small, tiny. We build a spacecraft the size of a postage stamp. It weighs only a few grams. It carries cameras, sensors, navigation equipment, and a transmitter, all etched onto a single silicon chip. And attached to this chip is a sail, a light sail. A sheet of material so thin it is barely there, yet incredibly reflective. We launch thousands of these tiny chips into orbit around Earth. And then, on the ground, or perhaps on the moon, we turn on the beam, a bank of powerful lasers combining their light into a single, coherent column of energy. The beam hits the sail. It does not burn it, it pushes it. Light has momentum. When it bounces off a mirror, it gives a tiny kick. With enough light and a light enough ship, that kick becomes a shove. In a matter of minutes, the laser accelerates the tiny probe to 20% the speed of light. 60,000 kilometers per second. At this speed, the journey to Proxima Centauri b does not take 70,000 years. It takes 20 years. A single human generation. Imagine the fleet of star chips, a swarm of glistening butterflies hurtling through the interstellar void. They are silent, they are cold, they are asleep. For 20 years they drift through the nothingness. Dust grains in the void strike them like bullets. Some are destroyed, some malfunction, but there are thousands of them. And then they arrive. They do not stop. They are moving too fast to slow down. They screen through the Proxima system in a matter of hours, but in those hours they wake up. Their cameras click frantically. They take pictures of the red sun. They take pictures of the planet. They swoop past Proxima b, closer than any telescope could ever look. They see the surface features, they see the canyons, they see the coastlines, they see the shadows of the clouds. And then they turn their antennas back toward Earth, the pale blue dot 4 light-years away, and they whisper. The signal is weak. It takes 4 years to travel back to us. So, 24 years after launch, we are waiting. We are listening. The great dishes on Earth are pointed at the southern sky. And then the data stream arrives. Image after image fills the screens, blurry at first, then sharper. We see a world, not an artist's impression, not a computer model, a photograph. We see the color of the soil. We see the glint of the rivers. We see the truth. If we see ruins, if we see geometric shapes, if we see lights, the history of humanity divides into before and after. But even if we see only rock and ice, the achievement is monumental. We have reached out. We have touched another star system. We have become an interstellar species. This is the scale of the commitment required by the 26 planets. They challenge us to be better. They challenge us to think longer. We live in a world of instant gratification. We want answers now. But the universe operates on deep time. The light from these stars took centuries to reach us. The journey to visit them will take decades. The evolution of life takes billions of years. To understand the 26 planets, we must slow down. We must adopt the pace of the cosmos. We must become like the cathedral builders of the Middle Ages, who laid foundations for structures they would never see finished. We are laying the foundations of the starships. We are grinding the mirrors of the observatories. We are doing it for the 26. Because they are there, rotating in the dark, waiting. Perhaps on one of them a creature is looking up at its own sky. Perhaps it sees our sun, a faint yellow star in its constellation. Perhaps it wonders if there are 26 planets around that yellow star. Perhaps it is building a telescope. Perhaps it is building a sail. Perhaps we are not the only ones looking. As we end this extended journey, let us hold on to that thought. The universe is vast, yes, but it is also reciprocal. Light travels both ways. Gravity pulls both ways. Curiosity looks both ways. The 26 planets are not just targets, they are mirrors. And as we polish the glass of our telescopes, we are preparing to look into that mirror and see, for the first time, who we really are. We are the watchers, we are the listeners, we are the travelers. And the journey has only just begun.